The idea of an infinite universe has roots in ancient philosophy and has evolved significantly over centuries. The ancient Greeks, particularly Aristotle, proposed a finite geocentric universe with a clear boundary. In contrast, Giordano Bruno, during the Renaissance, argued that the universe was infinite, filled with countless stars and planets like our Sun. His view was considered heretical at the time, but laid the groundwork for modern cosmology. Today, cosmologists consider the possibility of an infinite universe through theories like cosmic inflation and general relativity. Modern evidence, such as observations of the cosmic microwave background, CMB, and large-scale structures of the universe suggest a flat and possibly infinite universe. In particular, the notion of cosmic inflation posits that space expanded exponentially in the early moments after the Big Bang, possibly making the universe infinite in extent. Imagine a book that adds pages forever. Even though you can read only one page at a time, there are always more pages to turn, just as there may always be more universe beyond what we can see. Cosmologists use different models to describe the possible structure and extent of the universe. The finite universe model suggests the universe is closed and bounded, like the surface of a sphere, finite in size but without edges. The infinite universe model suggests the universe extends forever in all directions without boundaries. The key difference between these models comes from general relativity and how it describes the curvature of space. In a finite universe, space could be positively curved like a sphere, while an infinite universe would have zero or negative curvature. The Lambda-CDM model, the standard model of cosmology, currently describes a universe that is expanding and has a flat geometry, implying that the universe could be infinite. Flatness has been confirmed with high precision through Planck satellite measurements of the cosmic microwave background. A finite universe is like a globe. If you travel far enough in one direction, you will eventually return to your starting point. An infinite universe, on the other hand, is like walking on an endless plain, where no matter how far you go, you will never come back to where you started. The universe's shape, or geometry, is a fundamental aspect of cosmology, and is determined by the universe's total energy density. If the density is greater than the critical density, the universe has positive curvature, closed. If equal, it has zero curvature, flat, and if less, it has negative curvature, open. Each of these geometries leads to vastly different conclusions about the universe's fate and size. Einstein's general relativity links the shape of the universe to its overall mass-energy content, which includes matter, radiation, and dark energy. Data from the Planck mission indicates the universe is nearly flat, meaning it is very close to the critical density. This supports the idea of an infinite universe, although uncertainties remain. Imagine you're on a boat at sea. If the universe is closed, the sea is like a curved globe where you eventually sail around and return to the same spot. If it's flat, you keep sailing straight forever. If it's open, the sea is shaped like a saddle, where paths curve outward but never reconnect. The theory of cosmic inflation explains how the universe expanded exponentially fast in the first fraction of a second after the Big Bang. This rapid expansion smoothed out any irregularities, making the universe appear uniform on large scales. However, cosmic inflation also implies that the universe could be far larger and potentially infinite beyond the observable universe. The observable universe is limited by the speed of light and the finite age of the universe, meaning we can only see regions where light has had time to reach us. The observable universe has a radius of about 46.5 billion light-years, even though the universe is only 13.8 billion years old. This discrepancy is due to the expansion of space itself, meaning regions that were once close together are now much farther apart. Imagine blowing up a balloon, representing the universe. The surface area of the balloon expands quickly, and parts of it move beyond what you can see. The observable universe is like the part of the balloon you can still glimpse, while the rest may continue indefinitely. The multiverse theory suggests that our universe is just one of many, possibly infinite, universes. There are different types of multiverses. Level 1. Multiverse. In an infinite space, distant regions could exist beyond our observable universe with different initial conditions. Level 2. Multiverse. Universes with different physical constants may form through eternal inflation, where regions of space continue inflating, creating separate universes. Level 3. Multiverse. Based on the many worlds interpretation of quantum mechanics, every quantum event could split reality into multiple branching universes. The inflationary multiverse theory suggests that while inflation stopped in our region of space, it continues in other regions, constantly creating new universes. This could mean that an infinite number of universes exist, each with different laws of physics. Think of the multiverse like a bubbling pot of soup. Each bubble that forms represents a new universe with its own unique properties. Some bubbles are small and pop quickly, while others expand and continue to exist, just like different universes in the multiverse. Dark matter and dark energy are mysterious substances that make up most of the universe's mass energy content. Dark matter, which doesn't emit or absorb light, exerts gravitational forces that hold galaxies together. Dark energy, on the other hand, is a force causing the accelerated expansion of the universe. In an infinite universe, dark energy might drive this expansion forever, making the universe larger and more sparsely populated over time. The bullet cluster is an astrophysical example where the effects of dark matter were observed indirectly. When two galaxy clusters collided, the visible matter was separated from the gravitational effects, suggesting the presence of dark matter. Dark matter is like an invisible glue holding the galaxies together, while dark energy acts like a cosmic wind, pushing everything apart faster and faster. In an infinite universe, this wind never stops, and the expansion continues forever. In an infinite universe, quantum mechanics plays a vital role in shaping small-scale phenomena. Quantum fluctuations, random changes in energy, can have large effects over infinite timescales. Entropy, the measure of disorder, increases in a closed system, and in an infinite universe, entropy could reach a maximum state where no organised structures remain, known as heat death. Quantum effects, like the formation of virtual particles, could also play a significant role in the behaviour of an infinite universe. The Casimir Effect demonstrates how quantum fluctuations in the vacuum of space create measurable forces between objects. This is an example of quantum mechanics operating on small scales, but in an infinite universe, such effects might have profound implications on cosmic scales. Quantum fluctuations in space are like brief gusts of wind appearing and disappearing in a still field. Over an infinite time, these gusts might accumulate and create significant effects, just as quantum fluctuations could lead to the creation of new structures in an infinite universe. While some evidence supports an infinite universe, there are scientific uncertainties and challenges. One difficulty is that we can only observe the part of the universe where light has had time to reach us. The true extent of the universe is unknown, and there could be regions beyond our observation that change our understanding of its size and shape. Furthermore, quantum effects, the nature of dark matter and dark energy, and the universe's ultimate fate complicate our understanding. The discovery of gravitational waves from merging black holes in 2015 opened a new way of observing the universe. Gravitational wave observatories, like LIGO, might one day detect signals from beyond the observable universe, shedding light on whether the universe is finite or infinite. Imagine looking at a horizon on a clear day. You can see as far as your eyes allow, but beyond that horizon, there may be mountains, rivers, or endless plains. Similarly, the universe might stretch far beyond what we can observe, but we are limited by our cosmic horizon. The cosmic horizon is the farthest distance from which light could have travelled to us since the universe began. It represents the boundary of the observable universe. Beyond this horizon lies the unobservable universe, which may be infinite. This limitation arises from the finite speed of light and the age of the universe, about 13.8 billion years. However, space itself is expanding, so the observable universe is much larger than 13.8 billion light-years. The Hubble Deep Field image, captured by the Hubble Space Telescope, revealed thousands of galaxies in a tiny patch of sky, showing us how much more there is to see beyond our immediate view. Yet, even this only scratches the surface of what lies beyond the cosmic horizon. Imagine being on a boat in the middle of the ocean with binoculars. You can only see a small section of the vast ocean, but you know that the water stretches far beyond the limits of your view. The cosmic horizon works similarly. It's the limit of our perception, but the universe likely continues beyond it. An infinite universe has profound philosophical implications. In an infinite cosmos, anything that can happen, no matter how improbable, will happen an infinite number of times. This concept raises questions about free will, the nature of existence, and even the possibility of identical copies of ourselves in distant parts of the universe. The Anthropic Principle suggests that we observe the universe to be fine-tuned for life, because only in such a universe could intelligent observers exist. The fine-tuning problem considers why the constants of nature, like the strength of gravity, are exactly right for life to exist. In an infinite multiverse, it could be that we live in the rare universe where these conditions are met, while other universes have completely different constants that don't support life. The infinite universe is like a library with an infinite number of books, containing every possible combination of words. Somewhere in that library, there is a book identical to the one you're reading now. Similarly, in an infinite universe, there could be exact replicas of Earth, or even you, far away in the cosmos. Modern telescopes, satellites, and space missions allow us to probe deeper into the universe and gather data about its structure. Instruments like the James Webb Space Telescope, JWST, can observe infrared light from the earliest galaxies, helping scientists understand the universe's large-scale structure and whether it is finite or infinite. Gravitational wave detectors like LIGO and Virgo provide new methods to observe events beyond the reach of electromagnetic telescopes. The James Webb Space Telescope, set to observe the first galaxies formed after the Big Bang, will allow us to push the boundaries of how far back we can observe. The light from these early galaxies has travelled billions of years, offering clues about the universe's size and its possible infiniteness. Telescopes are like time machines, allowing us to look back at distant cosmic history. The further we look, the closer we get to understanding whether the universe stretches endlessly or has boundaries. In cosmology, mathematical concepts such as infinity are used to describe the universe's potential endlessness. Set theory, calculus, and topology help cosmologists model infinity, even though it may not be physically observable. For example, infinite series in mathematics provide a framework for understanding the endless expansion of the universe, while non-Euclidean geometry helps model the universe's possible shapes. The Friedmann-Lemaitre equations, derived from Einstein's general relativity, describe the expansion of the universe. In one solution, space can be infinite and flat, expanding forever. These equations are the foundation of modern cosmology and provide insight into whether the universe is infinite. Mathematics is like a map for the universe. Just as a map can show a large region we haven't fully explored, mathematical models allow us to predict and understand parts of the universe that we can't yet observe directly. Cosmologists propose several scenarios for the ultimate fate of the universe. In the Big Rip scenario, dark energy continues to accelerate the universe's expansion until galaxies, stars, planets, and even atoms are torn apart. In the Big Crunch, the universe's expansion halts and reverses, causing everything to collapse back into a singularity. In eternal expansion, the universe keeps expanding forever, becoming colder and more desolate over time. Observations of dark energy suggest the universe's expansion is accelerating, making the Big Rip scenario more likely if this acceleration continues unchecked. This would mean that galaxies, stars, and planets would eventually drift apart and disintegrate. The Big Rip is like stretching a rubber band until it snaps, representing space stretching until everything breaks apart. The Big Crunch is like a balloon deflating and collapsing in on itself. Eternal expansion is like a balloon that keeps inflating but never bursts. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. Inside a black hole, matter is thought to collapse into a singularity, where densities become infinite and the laws of physics break down. In an infinite universe, black holes may play a significant role in shaping the cosmos, and their interaction with space-time could offer insights into infinity itself. The event horizon of a black hole is the point beyond which nothing can escape. In 2019, the Event Horizon Telescope captured the first image of a black hole's event horizon, providing new insights into these mysterious objects. A black hole is like a drain in the fabric of space-time. Anything that gets too close gets pulled in and cannot escape. The singularity at the centre is like the point where all the water, matter, is crushed together in an infinitely small space. The Anthropic Principle states that the universe must have properties that allow life to exist, because we are here to observe it. In an infinite universe, every possible combination of physical constants may exist somewhere, and we happen to live in the rare region where conditions are perfect for life. This leads to the idea of fine-tuning, where slight changes in constants like the gravitational constant would prevent life from forming. If the gravitational constant was slightly stronger or weaker, stars would not form properly, making life as we know it impossible. In an infinite universe, there could be many regions where this constant differs, and life doesn't exist. Fine-tuning is like tuning a radio. You have to adjust the dial carefully to get a clear signal. In the same way, the universe's constants must be just right for life to emerge.